CS407, Numerical Analysis, Section 7.2, Runge-Kutta Methods. So, Runge-Kutta methods are designed to imitate Taylor series methods, without all the messy analytical differentiation. So, recall that we could solve an initial value problem using Taylor series. However, we needed to obtain x, x prime, x double prime, x triple prime, etc. in order to get that Taylor series. And that requirement can be quite a serious obstacle to using the method. In fact, doing the chain rule on numerous occasions can get messy real fast. You have to do some preliminary analytical work before writing the computer program, and ideally, really, you should be able to solve the initial value problem without doing anything more than writing code to evaluate f. And that's what the Runge-Kutta method does for us. So this section really focuses on the derivation of the Runge-Kutta method of order 2. Now that method's not terribly accurate, but it's good enough for real-time calculations on small computers, and in fact it's used in some aircraft as part of the mini computer that comes on board. In practice, you want a little bit more accuracy, and the Runge-Kutta method of order 4 gets used. Of course, the derivation of the Runge-Kutta method of order 4 is quite messy, so the authors present it without its derivation. So, at the heart of any method for solving an initial value problem is a procedure for advancing the solution function one step at a time. So, we might have a formula for x of t. So, a formula must be given for x of t plus h in terms of known quantities. And at the beginning, we only know x of a. The assumption is that f of t comma x can be computed at any point tx. And as examples of known quantities, we can cite x of t minus h, x of t minus 2h, etc. If the solution process has gone through a number of steps. Now, before explaining the Runge-Kutta method of order 2, let's talk about Taylor series in two variables. And yes, you can do Taylor series in two variables, but what you need is a tool called partial derivatives. Now, my sources in the math lab indicate that you won't get around to these until Calculus 3 at least, although Mitch Anderson indicates that he does a little bit of them at the end of Calc 2. Anyway, I guess for some of you, you'll have to trust me a little bit on this one. I'll explain what partial derivatives are, but I won't stress them too much. We'll just use them as a tool. The math department will do a better job explaining the theory and the theorems behind them. So the infinite Taylor series representation is f of x plus h, y plus k, this is for two variables, is the sum from I equals 0 to infinity of 1 over I factorial. Looks pretty familiar. But you get h times the partial derivative with respect to x plus the partial derivative with respect to y raised to the ith power, so, or the ith partial derivative of f of x comma y. Now these first few mysterious terms are, you have h plus k and partial derivative with respect to x plus k times the partial derivative with respect to y, and that's just f. This is the second one, it's h partial derivative of f with respect to x plus k times the partial derivative of f with respect to y. And when you go the second order, you're taking the second partial derivative with respect to x, and you're taking partial derivative with respect to x followed by partial derivative with respect to y, and then the second partial derivative of y. Now let's take a look at what these partial derivatives are. So suppose that f is a function, two variables, x and y. If we hold y constant, say y equals y0, then f of x, y0 is now a function in a single variable x. And its derivative at x equals x0 is called the partial derivative of f with respect to x. And it's denoted by f sub x, x0, y0. Similarly, the partial derivative of f with respect to y at x0, y0 is denoted by f sub y, x0, y0. The key point here is that the rules for differentiating a function of one variable work for finding partial derivatives, as long as we hold one variable fixed. Let's take a look at an example of how this is done. So, let's let f of x equal x squared y plus 3y cubed. Want to find the partial derivative with respect to x at 0.12, and the partial derivative with respect to y at 0.12. So the solution to this is the partial derivative with respect to x of xy. We differentiate x squared is 2x times y, and there's no x term in 3y cubed, so we treat that as a constant, so it's 0. Then we simply evaluate that at 1, 2. That's equal to 2 times 1 times 2 plus 0, and that's 4. Now, with respect to y, we differentiate with respect to y, so the first term, the derivative of y is a constant, or is 1, plus we differentiate 3y cubed with respect to y, that's 9y squared. And then we evaluate at 1, 2. So it's equal to 1 plus 9 times 2 squared, 1 plus 36, 37. So these aren't as bad as you initially feared. They do have uses in physics in terms of heat and wave equations. Anyway, back to our Taylor series. As in the case of the one variable case, if the Taylor series is truncated, an error term or remainder term is needed to restore the equality. And that error term is given here. Now the point x bar y bar lies on the line segment that joins xy to x plus h, y plus k in the plane. So basically your Taylor series in two variables is going to have the form given at the bottom. It's interesting to note that here the author switches between the partial differentiation symbols and the subscript notation. They're both equivalent, so don't worry about it too much. There are a couple of special cases in terms of f of x plus h comma y and f of x y plus k, which you can find on page 312 of the text. Anyway, let's look at the Runge-Kutta method of order 2, which is what we're here for. In the Runge-Kutta method of order 2, a formula is adopted that has two function evaluations of special form. K1 is equal to h times f of t of x, and K2 is h f of t plus alpha h plus beta K1. And the linear combination of these is added to the value of x at t to obtain the value at t plus h. So here we get, in this equation, we get W1 and W2. Eventually we obtain x of t plus h is equal to x of t plus W1 h f of tx plus W2 h f of t plus alpha h x of t plus beta h times f of tx. So it's a bit recursive, and what we can do from there after swallowing that mouthful of equation is we can have the computer do all the evaluations for us. And I for one welcome our new machine overlords, because I don't necessarily want to evaluate that. Anyway, the objective is to determine W1, W2, alpha, and beta, so the last equation is as accurate as possible. Basically what we want to do, or explicitly, we want to reproduce as many terms as possible in the Taylor series. So the Taylor series is given in the first sub-bullet, and the Runge-Kutta is given in the second sub-bullet. One way to force them to agree up through the term h is to set W1 equal 1 and W2 equal 0, because x prime is equal to f. This reproduces Euler's method, but as we saw in the last section, its precision is only 1, and we'd like to have a little bit better precision. A better choice of parameters in conjunction with the two-variable Taylor series yields the second-order Runge-Kutta method, and that's given below. This latter form shows that the solution function at t plus h is computed at the expense of two evaluations of the function f. Note that there are other solutions to this derivation, because alpha is actually arbitrary. And the error term for the Runge-Kutta method is given in the last bullet, and none of the Runge-Kutta methods of the second order Runge-Kutta methods is widely used on large computers, because the error is only O of h cubed. So you can see we do two evaluations there. So the Runge-Kutta method of order 4 is the one that is the most common use. Now its formulas are as follows. X of t plus h is equal to x of t plus h over 6, k1 plus 2k2 plus 2k3 plus k4. And k1, k2, k3, and k4 are given below. Even the authors of the text admit that the derivation of this is tedious. There do exist higher order Runge-Kutta formulas, but they're even more tedious to derive. As can be seen, the solution of x of t plus h is obtained at the expense of evaluating the function f 4 times for k1, k2, k3, and k4. The final formula agrees with the Taylor series expansion up to and including the term in h4. The error therefore contains h5, but no lower powers of h. Without knowing the coefficient of h5 in the error, we can't know the precise local truncation error. Researchers have delved into the subject, and there's been a large number of treatises written on this, but I think we can agree that we're better off than we were 4 orders ago, to paraphrase our political friends. Let's take a look at the pseudocode to actually implement this order 4. So here's the pseudocode, and as you can see, this pseudocode uses formulas we developed for the 4th order Runge-Kutta method on the previous slide. And again, we are evaluating f 4 times. To illustrate this pseudocode, let's see how it would work with the following initial value problem. We have x prime is equal to 2 plus x minus t minus 1 squared, and x of 1 is equal to 2. The exact solution to this is x of t is equal to 1 plus t plus tangent of t minus 1. What we can do is we can implement this as a driver program along with our procedure from the last slide and solve this problem on the interval 1 to 1.5625. Step size needed is calculated by dividing the length of the interval by the number of steps. In this example, we use n is equal to 72 steps. Pseudocode here includes an external function statement both in the main program and in the procedure RK4, because the procedure f is passed in the argument list of RK4. The final value computed for the numerical solution is 3.192937699, which is pretty good. So, general purpose routines incorporating the Runge-Kutta algorithm usually include additional programming to monitor the truncation error and to make necessary adjustments in the step size as the solution progresses. In general terms, the step size can be large when the solution is slowly varying, but should be small when it's rapidly varying. We're going to develop such a program in the next section.